Good day, weather technology students. In this video, we're going to talk about force balances and take all of those forces that we have that govern atmospheric flows, which include pressure gradient force, Coriolis force, centrifugal force, friction force, and gravity, and combine them into various force balances that will describe how atmospheric flow actually works. And so what we need to remember is we actually need to go back to Newton's second law, where forces equal the mass times the acceleration. And then ultimately, in a force balance, it's the sum of the forces per unit mass, at least that's how we talk about it in meteorology, so that we can sort of ignore or do a per unit mass thing, equals acceleration, where then the acceleration equals zero. Because to be in balance means that our flow is not neither going to accelerate or decelerate, but is flowing at a steady state, which is an acceleration of zero. Now, that does not mean our velocity is zero, right? Our velocity is just steady state. That steady state could be zero, but it could also be 10 meters per second, or 100 meters per second, or 150 meters per second. It all just depends on the exact force balances producing that particular flow. And so, again, just to recall, right, no acceleration. What does it mean that an acceleration is zero? That our velocity is constant, not necessarily zero, say like driving with cruise control on, and that ultimately there is no acceleration. We're going to begin with our first balance being our vertical balance, or the hydrostatic balance. The hydrostatic balance is a balance between two forces, the vertical pressure gradient force and gravity. Now, one thing to note here is that we're going to see this pressure gradient force appear in all of our force balance equations, at least for the purposes of weather technology, because it is the only force that can cause the wind to blow. And so what do we mean by a vertical pressure gradient force? What we mean is what is illustrated in our figure on the right-hand side. That with the pressure structure of the atmosphere, the pressure is greatest at the bottom of the fluid, or at Earth's surface. And as we go up, our pressure decreases. This inherently makes a vertical pressure gradient, right, or a pressure gradient in the vertical coordinate. And so that vertical pressure gradient force is going to be pointed outward, right? The flow is going to want to go from higher pressure to lower pressure and escape our atmosphere. But to a good approximation, gravity balances that vertical pressure gradient force, and that we largely don't have large accelerations of wind in our atmosphere in most scenarios. Now, there are a few scenarios where this would be violated. Can you think of some? What might be one example that has thunderous applause when it occurs? That's right, I led you to it. Thunderstorms, of course. Thunderstorms, we could actually see vertical accelerations, and this hydrostatic balance is violated. Historically, numerical weather prediction models, when they were first developed, made this hydrostatic assumption because, in general, it didn't directly predict thunderstorm activity. Our latest models, especially our convection-producing models, do not keep this assumption, because the atmosphere is actually not in hydrostatic balance in certain circumstances that are very, very important. Thinking now to our horizontal balances, one of the most common balances that we talk about, and that was talked about in Introduction to Meteorology, is geostrophic balance. Geostrophic balance is also a balance of two forces, our pressure gradient force, now in the horizontal, and the Coriolis force. And so the geostrophic balance is valid for straight flow in the upper levels, non-curved flow in the upper levels, because we are not considering centrifugal force or friction here. And so we illustrate an example here of this geostrophic flow in the diagram on the right-hand side. And so it's the geostrophic balance that is causing our wind to flow parallel to our upper level height lines. And so this is an example of a 300 millibar flow, because these heights would indicate a 300 millibar level. and that our pressure gradient force would want to push our air from higher pressure to lower pressure, or higher heights to lower heights if we're looking on a pressure surface here. And that Coriolis force will turn that wind, which is otherwise going to want to move directly from high to low, to the right in the northern hemisphere. That turn to the right in the northern hemisphere makes that wind flow parallel to our height lines. And so our height gradient here, our delta z over a distance, is what is indicated here by both our VG equation and our UG equation, which are equations that are meant to describe the geostrophic flow of the U component to the wind and the V component to the wind, recalling that wind is a vector. And so that's why we've noted it here in component form. Thinking strictly about pressure, right, our balance here, our balance of our forces equaling 0, summing our pressure gradient force and our Coriolis force. Again, we could substitute in height for pressure with some changes to our constant values here. We see that our G comes in favor of our rho when we're considering our change in our pressure surface heights. And so, for example here, this wind here is only going to be in the U component, right? Our flow is directed only in the east-west direction, such that that can be described just by this minus G over F delta Z over delta Y. Our delta Z would be indicated by the change in height values of our pressure surface, so that would be our 9,240 minus 8,880 meters. That would be our delta Z. And then that difference, that change in heights of our pressure surface, is occurring over a 500 kilometer difference here. And we would want to make sure we do our differencing in the same manner, so that if we did 9240 minus 8880, we'd want to do 500 minus 0. But if we were thinking more classically, if we were doing our typical XY coordinate system here, we would do 8880 minus 9240 with 0 minus 500. We just always want to make sure we're doing that differencing in the correct manner in order to get our sign to work out correctly. And the way we know the sign should work out correctly is that wind here is in a positive x direction. So our wind should be positive. So that means if we do 8880 minus 9240, that's going to be a number that's less than 0. So here we should have 500 minus 0. And let's go ahead and draw that out. We can assume that if we have an XY plot here, X and Y, here might be 0 on our X. Here would be 500 kilometers on our, our 0 on our Y and 500 kilometers. And we would want to make sure we do our differencing in exactly that manner. If we did 8880 minus 9240, it'd be 500 minus 0. Or if we did 9240 minus 880, it would be 0 minus 500. Now recall, this here, the units are in kilometers. These units are in meters, and we would want to make sure that those cancel out appropriately. So don't forget to consider units as we're doing calculations. But this is our geostrophic balance, wind that flows parallel to our height lines for non-curved upper level flow. When considering our gradient wind balance, we then are considering curved flow, again at the upper levels, because ultimately what we're considering here is frictionless flow. And so now we have two forces that are potentially balancing out our pressure gradient force. And in the example of this kind of low or trough indicated in our figure, our flow is again flowing parallel to our pressure lines or to our height lines if it's an upper level pressure surface and we're looking at the height of that pressure surface. Pressure gradient force always pointed towards lower pressure, balanced in this case both by Coriolis force and centrifugal force. That allows our flow to go counterclockwise in the northern hemisphere. Our Coriolis force would cause turning in a different direction in the southern hemisphere. Mathematically speaking, what does this look like? It looks like these two equations. Again, we have two components. We have our pressure gradient force here, our Coriolis force, and then our centrifugal force. That would be for the V components. And our u component would be similar, but with minus f times u and minus u squared over r. As a part of the homework assignment, you're actually going to solve this v equation, because really what we see here is a quadratic equation. And then we can solve to get an estimate for what our centrifugal flow, our gradient wind balance using centrifugal flow would be like. At the surface, we actually have to consider friction. Here we are looking at a slightly simplified surface balance where we are not considering curved flow. Even though our flow can be curved, if we consider a small enough segment, we can consider flow that is then ostensibly straight. Again, we have our pressure gradient force always pointed towards low pressure. But then because we know that the friction force is going to slow our wind down, that's going to diminish the ability of our Coriolis force to turn our flow, such that our wind is not going to be able to be turned parallel to our pressure contours, such that our flow is going to cross and go into low pressure, or cross and go out of high pressure around our highs. And so the way we draw this force balance diagram is, if we know we're at the surface and we know we have friction, we know our wind is going to cross our isobars and go into lows, so we would draw our wind vector crossing our isobars and towards lower pressure. The Coriolis force would always be perpendicular and to the right in the northern hemisphere, and our friction force will always oppose our wind. And that's how we draw this force balance diagram. Now, our equations get a bit more complicated because here now we get both u's and v's are two components in each of the equations, and it'd be more complicated to solve this system, although we still do have only two equations and two unknowns, so we would be able to solve this equation. Again, we have our pressure gradient force term here, minus 1 over delta P over delta X, our change in pressure over change in our X distance, plus F times V, minus K, our friction coefficient, times the U wind. And that would be one component of our wind, and another component would be related to our gradient in the Y direction. And so it would become much more complicated. Now, we give this one a particular name. We call it the Goldberg-Mohn force balance, or simply the surface wind balance. Either way of describing this wind balance would be okay. Finally, we want to talk about one more balance, which is really a balance of balances, and describes why we have a jet stream. And so, in general, we're looking at a vertical slice of our atmosphere here, with colder air to the north, warmer air to the south. This then produces different heights of our pressure surfaces. Cold air is more dense, which means our pressure changes more rapidly as we go up in the atmosphere. This creates then, at the upper levels, a very strong pressure gradient force. And so we have a combination here of our geostrophic balance with our hydrostatic balance, right? This fact that the pressure changes more quickly in the atmosphere is actually a result of our hydrostatic balance, but then that produces strong horizontal pressure gradient forces aloft, which then are the reason why we get strong winds or strong jet streams aloft, because we are now balancing this strong pressure gradient with a strong Coriolis force, giving air that will flow relative to this cross-section of our atmosphere. And so it just so happens, right, that lower pressure here is on the right-hand side, and so this is where our pressure gradient force would be pointed towards this direction, Coriolis force balancing this direction. The jet stream would be coming out of the page towards you in this given scenario. And so what is of particular importance here, right, is this slope of these pressure surfaces that give rise to a strong horizontal pressure gradient force at jet level, which then helps to produce through the geostrophic wind balance, in combination with this hydrostatic balance, a strong jet stream. That's it for our video on our balances. Thanks for watching.